Okay, so let's try to prove that this set of all ordered pairs, little g1 comes, they're all possible elements of this group, g1, and this little g2, that's all possible elements of g2. So with all possible ordered pairs, so the number of ordered pairs would be like mn. The order of this is m, and the order of that is n. Okay? So with this definition of the binary operator, let's prove that this set, with this definition of the binary operator, let's prove that it's a group. Okay? A group is always a set and its binary operator, a duo, a pair. Okay, closure. Start with closure. So the result of a binary operation has to belong to the set you're talking about. So in other words, we have to prove that this is a result. We have to prove that that belongs to this set. Okay? Well, how do we do that? Okay, look, GA and GB, they are both members of G1. Okay? So if I binary operate using the binary operator of that group, I will get some GC, let's say, that belongs to this group. Why? Because G1's a group, right? So it's closed. So therefore, little GA, GB will give me something that belongs to that set. So this belongs to that. So it's of that form. So that's okay. Now a similar logic applies here, because GX and GY both belong to G2. And you're performing a binary operation that belongs to G2. So the result of this will be some GZ, let's say, little GZ, and because it's a group, it's also closed, so the GZ you get here will also belong to that. Okay? So this result belongs to G1, and this result belongs to G2, so it's of this form. So it's closed. Okay, so closure, tick. Right? Now associativity, it's a bit tougher. So I'll use the book here, it's a bit tedious, and I'll write it all out. So we're trying to prove something like this. G1, let me try a different pen. See if it still works. So G1H1, binary operator, G2H2, no, I'm using old ones, hopefully they've, this one's not too bad, G3H3. Okay, so we're trying to prove associativity. So we're trying to prove that that is the same thing as if we had this bracket here. Okay? So now using this definition, let's rewrite this. So this then becomes, so this will be G1, G2, H1, H2, G3, H3. Okay. And again, using this rule again, so this becomes G1, G2, G3, comma, and then H1, H2, H3. Now, what we've got here now are elements of G1. These are three elements of G1. Right? Now, G1's a group. Okay. Therefore, these random three elements of this group are associative. So we can change the brackets around here. So we can call, so this will become just like G1 into G2, G3. And similar logic here, so this becomes H1 into H2, H3. Follow that? Okay. So, let's see. So this becomes G1, H1, G2, G3, H2, H3. Right. And you can expand this expands out, so this then becomes G1, H1, G2, H2, G3, H3. There it is. So this is this. So it's associative. Okay, so we've shown closure and associativity. Now let's try the inverse, the unit. What do you think the unit would be? Well, I suggest for the unit, so the unit would be something like this. The unit of G1, the unit of G2, whatever it is. Okay. Now, I won't go into too much detail. It's probably fairly obvious to you, right? So let the unit be this. So here, put the unit of G1 here, and here put the unit of G2. Now, so if you have unit, this will be unit, and that'll be unit, and what you'll get will be GB and GY. Because if that's a unit and that's a unit, all you're left with is that and that, right? Which is the same as this, and that's the unit, right? And similarly, if you put this the unit, if this is unit G1 and this is unit G2, and you multiply it, so you'll get that's the unit and that's the unit, leaves you with this and this. All right. What about inverse? Okay, how about inverse? Okay, so what's the inverse? What's an inverse? For every element, you have to have an inverse element, right, for it to be a group. So what's the inverse element of G1, G2? So G1, G2, inverse. What will that be? Well, here, try this. Seems fairly obvious. Okay, try that. Now, can you see that that's going to work? Because if you binary operate that and that, if you binary operate that and this without the inverse sign, you will end up with that. Can you see that? So you'd have like GA here, and here you'd have GA inverse. So that gives you GA inverse. So that would give you the unit. And here, this times the unit would just give you that here. So, so GX times GX inverse gives you gx inverse, that gives you the E. Okay? So the inverse of this is just that. So in a sense, you can say the inverse of the ordered pair is the ordered pair of the inverses. So, a manner of speaking. All right. So we've got inverse, we've got a unit, we've got associativity, we've got closure because this and this is of that form. All four properties are satisfied. Therefore, this binary operator defined on this group, well, this set, if you like, this Cartesian product, is a group. So we can now talk about direct product groups. Okay? Now, so what? Well, in particle physics, for example, there's something called the standard model. And it's pretty famous if you're a physicist, in particle physics particularly. And that model involves direct product groups. Right? In fact, there are three groups that get direct producted. So you have like group A, X, group B, X, C. And I won't go into details of what those groups are, but the basis of modern particle physics, the so-called standard model, uses a direct product of three different kinds of groups. And that triple, product of three groups, direct product of three groups, describes, to the best knowledge we have so far, until the Large Hadron Collider, hopefully in the next year or two, will give us new data and perhaps force us to change our ideas somewhat. Be very nice. Good physics, new physics. But anyway, up until today, 2012, the standard model summarizes pretty well everything, all the experimental data we have so far, pretty much. So direct product groups are very important. Okay, next topic will be the problem solving section. I think I'll do just a few questions. So I'll stop here for a moment.